In this lecture, we are going to discuss how we can use convolutional neural networks for sequences, specifically text. Although the type of CNN we are about to discuss will work just as well for generic sequences too. You might be wondering, how can this be? If CNNs are for images, how is it possible for CNNs to also work with sequences? First, let's recall the basics of convolution. The idea is this. You have an image which is the big square. You have a filter which is the small square. And you're going to slide the filter along each possible position in the big square. And at each point, you're going to multiply all the overlapping values and add them together, just like a dot product. Now, I know this is obvious, but it's worth taking note of. An image has two dimensions, height and width. There is also the feature dimension, but that's not an actual dimension which has correlation. And recall what I mean by correlation. If you have a picture of a red car, and you find a pixel in the image which is red, probably the neighboring pixels are also red. In other words, pixels beside each other likely have similar values. Now think of a sequence. Unlike an image, a sequence has just one dimension that is not a feature, time. So it's time instead of space. But notice one important detail. We have the same type of correlation in sequences. Data which are nearby other data in time are also close in value. That's why this appears like a smooth curve rather than just noise jumping around with random uncorrelated values. This suggests that convolution might be useful here as well. Luckily, convolution in one dimension is actually much simpler than convolution in two dimensions. Instead of a big square, we just have a big line, and the filter is the smaller line. Then we slide the small line across every position in the big line, multiply all the overlapping values, and add them together. Let's do a simple example. For the sequence data, we have 1, 2, 3, 2, 1. And for the filter, we have simply +1, -1. As an exercise, you might want to try to figure out the answer first before we move on to the solution. Okay, so here's what we get. At the first position, we have 1 times 1 plus 2 times -1, which is -1. At the second position, we get 2 times 1 plus 3 times -1, which is -1. At the third position, we get 3 times 1 plus 2 times -1, which is 1. And at the fourth and final position, we get 2 times 1 plus 1 times -1, which is 1. So essentially, exactly what we would expect. As with images, it's possible to express this operation as an equation. And remember that in deep learning, while we call this convolution, pure mathematicians and statisticians would call this cross-correlation. So just keep in mind that the sign is reversed. As an exercise, you might want to try and confirm to yourself that this equation does in fact implement the operation we just performed in the previous example. And remember that another thing we can do is add on features. So imagine X as a t by d array, where t is the number of time steps and d is the number of input features. Then imagine the output as another two-dimensional array of size t by m, where t is the number of time steps and m is the number of output features. Then W must be a three-dimensional array, t by d by m, and then we would have the equation that we see here. This is just like convolution with images. For a two-dimensional convolution, we have two spatial dimensions, plus one dimension for the input features, plus one dimension for the output features. So that's 4 dimensions in total. For a one-dimensional convolution, we have one time dimension, plus one dimension for the input features, plus one dimension for the output features. So that's 3 dimensions in total. As usual, While convolution might seem like an abstract concept, remember that there are multiple convenient perspectives on it that make it seem like things we are already familiar with. So one perspective is that it's just matrix multiplication, just like a regular feed-forward neural network, except that we have shared weights in order to take advantage of the special structure and correlation in the data. Another intuitive perspective is that it's just a sliding dot product, and the dot product is just a correlation finder. Correlation is just another name for pattern matching or similarity. So really what we are doing is asking, is this part of the sequence similar to my filter? And thus the filter becomes a pattern matcher or a pattern finder. All these concepts that you learned about convolution before still apply here. Alright, so now that you know how convolution works with sequences, how do we apply these to text? Well, luckily, when we use embeddings, that already gives us exactly what we need. For one-dimensional convolution, we need an input, which is a t by d sequence, where t is the number of time steps and d is the number of features. And of course, this is exactly what we get after we pass our sentence through an embedding layer. We go from a length t sequence of words to a length t sequence of integers, to a length t sequence of d length vectors. Since we have t vectors, each of length d, this makes up a t by d matrix when you stack them all together. And thus, we have exactly what we need to build a CNN for text. So here's how it all looks in code. First we have our input, that's a length t sequence of word indexes. Then we have an embedding layer. The output of that is a t by d sequence of word vectors. Then we have a 1D convolution. This is just the conv1d class. Then we follow the same typical CNN architecture, where we have convolution followed by pooling and so forth. So the same pattern applies here that we had for images. Generally speaking, the data shrinks in the time dimension, but grows in the feature dimension. So that's why you see the number of feature maps getting larger and larger. Once we're done that, then we can do a flatten, or we can do a global max pooling, which will give us a single vector of size M3. Finally, we pass this through one or more dense layers to get a single scalar, assuming we are doing binary classification. As you can see, this is no different from a CNN meant for images, except that all the convolutions and pooling are one-dimensional instead of two-dimensional.